I'd like to introduce the panelists. First of all, I'd like to introduce Nicola Paperno. Of course, all of you are familiar with his papers already, but he's an assistant professor at the University of Toronto. He received his PhD from Penn State. He spent some time at Google Brain, and he's extremely well known for his work on adversarial attacks to neural networks. The second panelist is Pinyu Chen. He is part of the Trusted AI group at IBM TJ Watson. He got his PhD from Michigan, and he's well known for his work on black box attacks on deep neural networks. As was mentioned, Bo Li is not here, but I'll introduce Bo Li. Bo Li is an assistant professor at UIUC, working or leading the Secure Learning Lab. Bo received the TR-35 and is well known for work on robust physical world attacks on for deep learning visual classification. I think there's a highly cited paper on that from 2018. These are our panelists, and there have been a few themes that have been sketched out for us. I'll go through those, and then I'll look to Pinyu and Nicola to elaborate on some of the questions that that we might be able to explore during the breakout session in a few minutes. So the first theme is it's titled Adversarial Attacks, a True Threat to Real-Life Applications. Of course, many of us work in academia, and we want our work to be, well, many of us want our work to be as useful as possible. We don't just write papers for our health. We want to actually positively impact the world. And so I think actually a few of the presentations associated with this session discussed actual adversarial attacks in the physical world. Actually, Bo Li's work involved some of this. Like, I think one of the really compelling applications was changing a stop sign, the recognition of a stop sign by placing stickers on the sign. So that's one consideration that we would like to discuss. What are these real world applications? What should really be keeping us up at night? Actually, maybe I'll pause on this one just to get some of the input from Pinyu and Nicola on that question to help frame our breakouts, and then I'll move on to the other two that have been laid out for us. Why don't you kick us off, Pinyu?
Yeah, so I can share my thoughts. So first of all, we have to agree our system, most of our system does not really require an attacker to show how dumb it is, right, or to break the system. But right. That being said, I think we need the adversarial notion in many senses, right? So and I think this adversarial attack is a very interesting word because we are not really attacking to gain benefit or show malicious purpose. I'm now viewing it as a kind of necessary thing to, especially to help us develop a better model. And you do see this introducing this notion of competition or an adversary in this model development actually helps machine learning original goal, right? A very typical example would be GANs, right? So you introduce a discriminator while you are generating images and try to discern whether the generated images are real or fake. So by introducing this competition, you eventually get a very good generator that can generate photorealistic images. So I think this is one typical example where you can think of this discriminator as a way to attack or find these vulnerabilities in your system and help your system to adapt to a better position, right? Than compared to the version without adversarial training. And also in terms of model developers' perspective, most of the time, so for me at least, I'm very curious when I first step in this field. I was very curious, like how come a model can achieve 99% accuracy on the test set, but a slight perturbation will kind of mess up everything, right? So if you are a machine learning researcher, you will say, hey, how come my model does not generalize, right? And I already separate the training, validation, and test set, but how come these things still occur? So in my perspective, I would view this attack as a way to do kind of ethical hacking, or just to find bugs in our system, or find bugs or these blind spots in our model and help improve our model. So they do not necessarily stick to the notion of attack in the security sense. And that's why I kind of step to the robustness region that includes generalization and also like more generalizable AI, if you want to frame it that way.
Yeah, I think that's a really good point that you make. I think a lot of people, when they hear adversarial attacks, they think of an adversary, but in reality, nature is really the adversary. And actually, in our application to the TaxiNet domain, where we're trying to taxi on an actual runway, we didn't have a sensible like observation model or sensor model for that, right? It's an image sensor. We have no idea how to specify that. It's much easier to specify like epsilon balls of allowed image perturbation, and with the aim of having that be a proxy for a model that we can't easily specify. Nicola, what are your thoughts?
So thank you so much for the leadway. I was going to discuss sort of what we define as robustness.
Yeah.
So I think sort of in the last couple of months, there's been sort of some consensus in the community around the fact that we don't really have a good way of defining what we mean by a robust model. And so the p-norm sort of discussion is probably the most sort of active, where it's clear now. We have a couple papers, including one that I co-authored, where basically we show that if by increasing the robustness to p-norms, basically, or I should say perturbations that are constrained by p-norms, you're basically harming the generalization of the classifier. And so it's clear that it's not the right definition. The problem then is, what is the definition that we should work on? And sadly, I don't have a good answer to that, at least not yet. I think definitely.
Well, that's why we have this Lorentz workshop, and we'll figure this out during the next half hour during the breakout session.
Yeah, and I think one source of inspiration for me has been sort of the work in privacy preserving ML, where you think about something like privacy, and it's very subjective, and yet sort of differential privacy sort of is establishing itself as sort of the way to reason about privacy, at least in ML systems. It's very nice because the fact that you sort of have this guarantee, which is worst case, sort of the privacy guarantee, gives you some advantages in terms of the average case generalization. So it's very rare that you have this synergy between sort of the security goal and the performance goal, where usually it's, you say like, okay, give me like a couple of points of performance and I'll give you some security property. Here it's very well aligned. And so I'm very hopeful that sort of we can draw some inspiration from this whole area. And it's not sort of random sort of thing that this definition sort of stems from the crypto community. So you can really see sort of the crypto touch on this line of work. And I think if we sort of try to draw inspiration and reason about robustness under that lens, it will most likely help us sort of make progress. Otherwise, if we sort of continue down sort of the p-norm path, it's going to be sort of a cat and mouse game for a long time, just like many areas of computer security. And I completely agree with sort of the adversary versus no adversary. And often I like to say, like, even if you don't think sort of someone would craft adversarial examples, you should sort of care about them if you have any sort of worst case consideration. So anything that involves safety is, of course, a great way to sort of test the systems.
Great, excellent. So you foresee maybe greater collaboration between robust ML and the security communities. What do you think are some of the challenges in bringing those two areas together?
So I feel like the ML community is very benchmark driven, and so very good at coming up with algorithmic innovations once there's an established way to evaluate things. And currently we have lots of recommendations how to evaluate adversarial examples, but they don't there's not like a clear sort of benchmark approach that you can follow like you would for sort of evaluating generalization. So this is sort of, I think, an issue. And then one thing is, in the security community, I feel like there's a lot more sort of systems-oriented work where the some of the papers are typically written by people who are like experts in a specific area and will try to reproduce sort of a more realistic setup. Whereas sort of in the ML setting, we're typically sort of taking off-the-shelf benchmarks and architectures and trying to sort of improve upon them. So I feel like collaborating with sort of application domain experts will help a lot sort of discuss the robustness. I don't think we can sort of discuss it very abstractly until we have some concrete use cases. So for instance, there was some very nice work from Florian Tramer from Standford, who was sort of showing how you can attack sort of things like ad blocking extensions with adversarial examples. And so this is kind of a nice, I think, piece of work because it shows sort of a realistic threat model where you might care about adversarial examples. And so finding more of these, I think, is going to help us sort of move away from sort of artificial definitions. And I think it's good that we're at this stage because the reason we introduced the p-norm sort of constraints, like back sort of when we were initially working on this, is we wanted some sort of toy problem that we can tackle.
Yep.
And now, like, thanks to the interest, sort of the community has grown so much that now we know how to sort of address this p-norm threat model. Like, there's lots of great work that people have done to train models with these guarantees. And so now the question is, what is the actual guarantee that we should care about now that we've sort of achieved this baby step?
Excellent. Great. Maybe we'll move on to the next theme here, which is how can empirical verification be used in an industrial qualification certification framework? So maybe we'll start with you, Pinyu.
Yeah, so the question is how empirical verification can be used in industrial scale. Yeah, so I can share some of my
or
thoughts.
Certification. Yeah, this is basically what your talk was about.
Yeah, so it really depends on who your clients are, right? So in industry, some clients are very getting used to these AI products, right? Especially tech companies. But on the other hand, there are a bunch of industrial sectors that are just getting ready to start their digital transformation, and they just want to have a flavor of how AI can help improve their offers or products, right? Like finance industries or insurance companies, where they would require very high explainability, and they are relatively conservative because of all the law regulations and these clients' satisfactory stuff. And that being said, they just started to test out their models, but they are still very curious to see where this AI model would go wrong when they deploy their model as part of their solution, right? So they always have their favorite and traditional model they know pretty well. Like it could be like a logistic regression model or even a simpler linear model. They know everything about that. Now they are trying a new AI model, try to replace that original model. So I think this is an interesting moment where we can show, okay, when you are testing your model, do you want to consider these potential risks, right? Like adversarial examples. So I like to think of this adversarial example in this industrial use case as like a proof by contradiction, or like show as an example to convince the model developers or these people who are using their AI or practicing AI in their offerings to take a look at those adversarial examples. And so they first understand, okay, this is the example that should not go wrong, but somehow this new AI model makes it wrong. Then how do I fix it? What kind of bias or non-explainability will incur when we try to deploy the AI model into their solution? So I think this is a very good use tool. Just even before tell them how to certify a model, just show them by example, like these are the examples that are likely to be misclassified. How are you okay with it, or you think it's a problem that needs to be fixed? If they think those adversarial examples that should not happen, then we can bring in more model hardening or defenses to help them solve the problem. And I think that's the kind of the roadmap in my head, and that's the experience based on what we talk to our clients.
So the adversarial examples are of course examples of failure, and I guess as the development continues, you'll find hopefully you'll find fewer adversarial examples, but it's not really a proof for it. How do you translate an approach that finds failures into trust that you actually do have a good system?
Oh yeah, yes.
Does that make sense?
So, yes. So the bridge happens. So first, the way I often tell them is, okay, you have a model you want to deploy, right? Then I'm going to run some robustness testing for your model. That basically means generating adversarial example. And this black box attack can really come handy in the sense that clients have their own model and they are reluctant to share the details of the model because they believe there's a high IP value, and also, of course, there are other concerns about it, training data leakage or so. So that kind of motivates us to start from this black box attack first, because the clients are more comfortable to offer a kind of an entry point, right? Like through a cloud service, right? For us to remotely test the robustness of their model. And there's also a benefit of a model, an attack being black box, so you can get rid of the dependencies on the platforms, right? Because you don't really need the backpropagation through TensorFlow or PyTorch per se. You can remain maximum independence when you do this black box testing. And so once you show, okay, there are some adversarial examples I found in your model, they will say, okay, can you fix it for me? And this is the place where we invoke these defenses, right? You can use adversarial training, you can use data augmentation. So you train a new model for them. Then how do you convince the clients, okay, this model is better than your original model? This is where the place that the certification or verification will come in. So you can provide some scores like certified bonds, like our clever score or whatever score, to show, okay, based on this notion of the robustness score, your model has been improved from 20 to 50, something like that. So you can make everything quantifiable and show by example to make them understand what we have done and what vulnerabilities their original model have in terms of adversarial examples. Yeah.
Great. Nicola?
Yeah, I would say, so I guess as usual in the panel, I agree with everything that has been said before. And one thing I want to emphasize also is I feel like we don't have very good ways to manage sort of the life cycle of the models, or to have some sort of model governance, where once you deploy the model, you want to also identify some of these failures sort of systematically. And so one thing that didn't sort of converge yet, I think, is how to handle sort of producing well-calibrated uncertainty estimates. So that seems sort of very important, and also in regards with the training data that you have for your model, and how to provide a good characterization of how much the predictions are supported by the training set that you have. And so I feel like this can also help with the efforts that we describe, where once you have sort of a high uncertainty prediction, you will sort of use that as a test case that you can sort of evaluate your model on, and then also maybe sort of change your approach to better capture this, or maybe collect more data and so on. And so this
better
is also,
estimates for like out of distribution.
Yeah, because like most of the models we use, I mean, maybe I don't have a good understanding sort of in some industries what people are using, but what I've seen a lot is just like more or less variants of sort of softmax based sort of cross entropy models. I mean, either logistic regression or deep net, or usually the objective itself doesn't let you say that you don't know how to classify or how to predict on the input. And there is not really a good sort of de facto approach for how to handle this. And I feel like this is sort of important because we're now saying we train a model on a specific distribution, but the model has no way to say that this is not the distribution I'm supposed to be predicting on. So that seems very important, especially in safety critical applications. And then one thing is I would like us to get to a point where the technique allows us to have sort of iterative approaches to designing the models, where right now it's sort of we train a model, we deploy it doesn't work in certain cases, we fix some aspects with the training, and then we start sort of training the model from scratch again. And so there's a lot of interesting things to think about, sort of how to improve sort of online learning in the sense where you can now not only add things to your model, but also remove things. So things like machine unlearning are interesting to think in that regard, where you might realize that one of your training examples was not sort of a good training example to include in your training set. And so now either you start training from scratch, or if we had better approaches for unlearning, you could simply sort of fix that and patch the model in some ways. And I feel like this is something that people do in software, and we don't have a very good way to do this in sort of in ML.
Great. All right, so the final theme is where lies the balance between AI architecture complexity and vulnerability to attacks? Where is the balance between complexity and vulnerability? Maybe we'll start this one with you, Nicola, and then we'll go over to Pinyu.
Can you say the question again?
Where lies the balance between AI architecture complexity and vulnerability to attacks?
Right. So I guess as far as adversarial examples are concerned, it's sort of the evidence seems to suggest that all model classes are sort of affected by the issue. And a lot of results seem to be pointing to the fact that if we want to learn a robust model, then we will need sort of either better features or better data, in the sense that we would need more data. And so that seems to suggest that sort of we will have to use sort of more complex model classes to be able to train a robust model. Even though, I guess from the interpretability perspective, having simple models always has this benefit that you can sort of provide with explanations that are sort of more straightforward. Although I sometimes wonder about this, if it's kind of a philosophical discussion. Like, it's like, if we cannot write the program ourselves to solve the problem, why do we expect that we would understand what the machine learning algorithm would come up with, right? So it's kind of a chicken and egg problem to me.
Yeah.
But
also, like a 5-layer network isn't that much more explainable than a 100-layer network.
Yeah, and I don't agree with like the fact that decision trees are explainable, because like if you want a decision tree for something that a deep net is solving, then you're more likely looking at a random forest with I don't know how many branches in each tree. And so it's just as easy to follow neurons and sort of understand for each neuron, it had these inputs, that's larger than 0, so I output this. I don't see how that's more complicated than like following a tree and saying like this value is bigger or smaller, and therefore I'm going to that branch. Yeah, so that's another box though.
Great. All right, Pinyu.
Yeah, so I think this is a great question. And recently we have seen some evidence that both empirically and theoretically, like if you want to make your model robust, maybe your model should be wider, right? Or but on the other hand, if your model goes deeper, your standard accuracy may be better, but is usually less robust. So yeah, so this is a very interesting question. We kind of investigate a while ago, right? So like in 2018, we kind of take 18 available ImageNet models, and then we kind of benchmark robustness versus accuracy, and we found some undesirable trend, right? So the later model becomes bigger and more complex, and with a better top one standard accuracy. But on the other hand, they kind of become more sensitive to input perturbations and make them less robust. So I would think this is if you care about robustness, right, and practical deployment perspective, you really, when you design your model, you should not only just care about standard accuracy, you should also care about the robustness into the picture and design. So I'm also very happy to see there are a few recent works that starts to search for better neural network architecture with this robustness objective function in mind, right? And so really going beyond accuracy and step into this robustness notion. And I think if we as a community spend more efforts on finding a better neural network architecture or better training strategy, this trade-off between robustness and accuracy can really be improved a lot.
That's great. Thanks so much, Pinyu and Nicola. I think we are right at the time where we should be going into our breakout sessions. So, yeah, maybe we'll start with you, Pinyu. What were some of the key takeaways from your discussion?
Yeah,
to help see the broader discussion as part of this session.
Yes. So we have a very interesting discussion, and we are also very fortunate to have Bahid in our group, who gives from OD group, and they gave a very interesting talk and a very valuable lessons from industry, especially OEM's perspective in terms of I would say real-time certification, right? So we all somehow happen to feel a little bit pessimistic about the current verification technique because of the scalability issue, because of the complexity of the neural network. But and we talk about whether to use a shallow network in replacement of a deep neural network to simplify verification. But even with the shallow network, in addition to the performance degradation, it's still very difficult to reach this real-time certification, right? So, and I think there's an interesting thing I observe and kind of summarize is that maybe there is a scenario where we can mix this empirical robustness and certified robustness together. So in the offline scenario, maybe we can use these verification techniques that would take longer time, but it's more provides a better certification power to certify off-the-shelf model offline. But in terms of this, when the model has been deployed, right, like autonomous driving car, when it is on, you also need some real-time or runtime verification to make sure the vehicle is in a stable state. In that scenario, maybe it makes more sense to invoke these empirical robustness techniques, like generating different testing scenarios to make sure your vehicle is in a good state and it satisfies all the safety requirements. So real time, maybe it's empirical robustness is more useful, and offline, maybe certification tools are very more applicable. And we also
before you move on from that point, can you or someone from your session clarify what's actually meant by real-time verification? And so you mentioned this use case or broad application domain of automated driving. What would be something that you would want to verify, and what happens if it's not, if it comes back not satisfied?
Yeah.
So what's the utility of that, and what's the time scale?
Yeah. So we have, so we didn't really talk about the specs yet, but we do have this notion of, and both Joseph and but he mentioned in the future ISO standard, when the law regulation, they actually allow failures in the machine learning driven system. So when we talk about verification, that means it may give us an easier task in the sense that we have the opportunity to allow failure, but we have to embrace those failures and observe those failures and have the ability to correct those failures. Eventually, we are still looking for some sort of probabilistic certification notion. We have this notion of with probability 1, this vehicle at this current state is stable. And to make this a real-time verification, right? We have to generate a lot of scenarios at the same time and make sure this system would not go wrong, or most likely would not go wrong in those scenarios. So I think this real-time means it has to be like we think this vehicle or based on the environment, it has to be like adaptive to the real-time scenario to make efficient control and to ensure safety, especially for autonomous driving. So I think we are really talking about this very short time response verification here.
The story goes something like this. It's probably really tricky to completely validate or verify a machine learned system. So what you do instead is you incorporate a runtime monitor that monitors the behavior of your machine learned component. That runtime monitor can switch to a non-machine learned component as like a fail-safe measure. Mm-hmm. And what you do offline to present to the certification authorities or whatever is a safety case that's based on the conglomeration of your runtime monitor with your machine learned component and your fail-safe system.
We also, one interesting question raised by Lisa is the liability issue, right? So even though once we provide those certifications, right, if there are still some accidents happening, who is responsible? And then we kind of have some discussion on that. Like when will a driver be responsible in the autonomous driving mode? And so, and also I think we have very interesting discussion in terms of this whole infrastructure idea, right? So again, Bahi mentioned that there are some countries that when they are using autonomous driving, they are actually deploying this IoT, Internet of Things devices to help better autonomous driving. And in that sense, hopefully, because of this active notion of robustness certification, maybe the whole system, including the infrastructure, is easier to certify compared to a passive setting where you are just building an autonomous driving car, but you don't update your infrastructure. I think that's a very, very interesting perspective.
Yeah.
Yeah. And
great.
Yeah.
All right, Nicola, what were some of the key takeaways from your breakout session?
Right. So we discussed. So we first started going on a diversion about p-norms, and then we were reminded that we had the topic to discuss during the breakout. So we got back to sort of the theme around certification, and I think in some ways, sort of the discussion we had around p-norms, we agreed that it was sort of the prerequisite to define sort of what is the acceptable behavior of the system. And so we had some interesting discussions where it seems that on one hand, if you rely excessively on the p-norm, you might get a false sense of security. And there was an interesting comment made that a lot of NeurIPS submissions sort of mentioned in their impact statement that essentially following blindly sort of approaches to increase robustness to p-norm perturbations might give you a false sense of security when you're deploying in the real world. But that on the other hand, adversarially trained models seem to have sort of some nice feature visualizations and so on, and in some cases better generalization if the adversarial training is not sort of overdone, that the guarantee you're trying to prove is not too large. So it seems like it's not it's not like we want to completely discard the p-norm. And that in particular, if we had a better way to specify multiple radii rather than a unique radius common to all the points, that would probably give us sort of some way to make progress. Then we discussed a lot the role of uncertainty.
Okay, can we dig into that just a little bit more? Because this theme came up a bit in our breakout session as well. So many of the applications we're interested in, it's not just like a static task of like classification or something like that, but rather it's like a sequential task, like the control of an aircraft or a car or something like that. And if we use a p-norm, it's really tempting to apply that p-norm time step by time step. But what often happens in real environments is that there's correlations across time in terms of the perturbations. So Giant mentioned like bird poop on a sensor or something like that. So how do we come up with these more realistic correlations across time?
So I'm not the answer to that, but it is a good point. It's also the fact that when you look at sort of the perturbations for things like language models that are processing sequences,
right,
depending on sort of the position of the perturbation, it can have sort of a different effect on the outputs of the model. And if you're trying to, for instance, do some sentiment analysis, this is interesting, where depending on where you insert the perturbation, you might have to introduce more or less perturbations. And so, yeah, I'm not sure I have a good way to model sort of the dependencies across time steps, but it's definitely, it adds some complexity. It's for instance, in reinforcement learning.
Mm-hmm.
Yeah.
Maybe we'll just pause here for a moment, just in case there are some in the audience who have some thoughts on either problems or solutions related to defining robustness.
I have some comments. Like,
yes, please go ahead.
You guys talked about like the setting of controllers and also reinforcement learning, and I think one challenge in that setting is like how you define the possible set of perturbations. Like definitely LP norm is probably not the best way. Like if suppose I have a controller, the controller has different types of input. Like I have positions, velocity, like angular velocity, those kind of things are quite different types of variables. And I guess you cannot directly apply LP norm kind of thing to that kind of input. It's not like an image, like every pixel is equal and it's just pixels. But we know we have like different meanings for each feature, and we don't know like maybe this feature is more sensitive, and you can't make it too robust, because if it is too robust, you cannot control the system. But maybe some other features are not that sensitive, you need to make them robust. So it's very hard to decide like which what is the right threat model to consider.
I think you're muted, Mykel.
Thank you. It's kind of interesting. Like we're using machine learning approaches in the first place because we don't know how to define these decision boundaries in a very high dimensional space, right? That's why we're using machine learning. And now what we're doing is we're trying to define a different decision boundary, also in the same super high dimensional space of allowed perturbation. And the reason why LP norms are so nice is because we can define those in terms of one parameter, right? The radius, right? Yeah. And now how do it seems like we're back to solving another problem that seems to be maybe about as hard as the original task.
Yeah.
That's a bummer.
If I may add something
yes,
on
the bird poop.
No, it's in a more serious note. It's in fact at some point, if we want to convince regulation authorities, you have to answer really a question that they are asking. So for your system, it would be what could be your hazards or your perturbation that could occur, or the failure that could occur on your system, and what are the consequences for the inputs of your model. And then, okay, try to demonstrate that you're robust to this kind of perturbation, this kind of hazards. So at some point, okay, you need to make a translation into mathematical norms or metrics, of course. But I think in this case, we need to go back to the system definition, system safety analysis, define what are the perturbations or problems that could occur, and then that would be a bit maybe tricky. Make the link with the mathematical and the norms that could occur for your inputs. But and also you will rely on the completeness of all the perturbations that you will describe. If you forget something, then that's something that is usual in system safety. You do your best to cover everything, and that's I think how we should try to cover every possible problems and then make the model robust to that.
Yeah, one thing we mentioned related to this in the breakout group is that a lot of progress in ML when learning from little supervision was done sort of by doing data augmentation or assuming that labels are consistent according to specific transformations. And so this might be an avenue to sort of explore that thought that we've been discussing.
Great. I think, Mark, you had your hand up?
Yeah.
Great.
Just a small follow-up on the discussion we just had. So I think there is fundamentally two problems. So the one problem that was just discussed before, that's, okay, we need to find a realistic threat model, and then, or we first need to say, okay, these are the possible threats to our model, and then show what could happen to our model under these threats. And the other one you, Mykel, mentioned is like the sequential nature of the decision making and how sequences influence each other. I mean, so Juan Zhang here in his video, he showed this verification for reinforcement learning. And I happen to do a similar project. And what I found there is, let's say LP norms are a reasonable perturbation. So then you can certify that for a picture input, your reinforcement learning controller is robust to a perturbation on 99% of states. But the issue is, this might not be the 99% where it matters. So if you're playing Pong, most of the frames, it doesn't matter that you're robust. Same thing if you're driving a car. If you're on the highway, it might not matter if you make a slightly wrong decision according to some metric in one frame, but if you're overtaking a car or if you're in a curve, then it's important. So we somehow need a notion of these dynamical models, when it's important to be robust and how states influence each other through time.
Great points.
I think actually what Mark just said is a good lead-way into what we discuss next, which is basically how to capture the uncertainty of a model when making predictions, and to understand sort of what you want to do about these test cases. And one thing that was interesting we mentioned is the approach to randomized smoothing already incorporates this abstaining option. And so this is interesting because in the process that you're using to certify sort of the robustness of the model, you're saying sort of I take the point, randomly perturb it many times, and then look for consistency of the label. Then here, if you don't have something that is statistically meaningful in terms of the vote across all of the points that you've sampled, then you can decide to abstain for that point and to say that you don't know how to certify it. And so that's, I think, interesting and shows that there is a good connection between the certification and the uncertainty. And then afterwards, we sort of discussed sort of whether we should consider adversarial examples as something that is different from out of distribution detection, or if it's sort of the same problem where there's some inputs that are on, off the manifold, and so on. And there was some good points brought up with sort of the airline industry in mind, where there's a lot of simulation, and you might care a lot about physical perturbations more than sort of some of the attacks that we've discussed. And so we sort of finished discussing sort of what would be the once we have a result on the simulation, what would it take to then take it to the real world. And another point we brought up was the difficulty in solving the problem, coming back more to the out of distribution question, by having sort of a generative model, and why that's very hard to know the distribution first.
So when you say generative model, you mean, can you clarify what you mean by that? Because I think there are a number of different definitions for that floating around the community.
Having a reliable way of sampling from the distribution, having good understanding of what the distribution you're looking at is.
Yep.
And so that would solve a lot of problems that we've been discussing today, but it's unfortunately very difficult even for very simple, or at least what we think are very simple data sets.
Yeah, so in cases where you do have this generative model or some kind of rough approximation of a somewhat acceptable model, it can be super useful. So in our work on aircraft collision avoidance, we put a lot of effort into building this kind of generative model that captures the behavior of pilots interacting in the airspace and so forth. And once we had that model, we were able to frame the problem of finding the most likely failure, right? So in contrast with much of the discussion that we've been having about adversarial attacks, in that discussion, the uncertainty is basically an interval or a region. And we're just happy finding any point within that region and finding a failure. So sometimes we just call that falsification. But the approach that was of interest to the FAA and the International Civil Aviation Organization and the general international safety community was, sure, we can come up with these failures where aircraft collide, but it often involves, very unrealistic sequences of pilot behavior. And so what we really want is to really characterize what are the most likely failure modes of the system. And you can really only do that with a measure of likelihood from using this kind of generative model that you mentioned.
Yeah, I think that's like, it's where, like, I think the part of the problem is, again, what I was saying before we went into the breakouts, is sort of the approach of sort of the ML community, where you're relying heavily on benchmarks, and in practice, when you're looking at a system, you might not care equally about all of these test points, and so just measuring the average performance doesn't make as much sense. Yeah.
Great. So there were a few key takeaways from our session. Chonglu started the discussion with the importance of combining these machine learning and security community approaches and the challenges associated with that, as Nicola mentioned in the opening remarks. Unfortunately, we didn't have anyone in our session who was from the security community. I don't know if there's anyone online right now who can speak from that perspective, which is more from a systems-oriented perspective. Okay, mostly a ML audience here. All right, we also spent a bit of time talking about the challenge of deciding what are appropriate perturbations. We of course discussed P norms, how we need to choose wisely, what allowed perturbations are allowed, what perturbations should be allowed, and how to capture safety as well as other maybe operational performance considerations. One point that Giant made was that as we go to fix one area to make it more adversarially robust, it may result in trade-offs in other areas. So if you fix one area, then maybe problems pop up in another area. And it seems like, well, one of the key challenges in engineering is balancing multiple different considerations, right? I think this is one of the most fundamental concepts in engineering. And it seems like we really don't have good tool sets for facilitating that. Another major point was, or this was a longer topic of discussion, how to incorporate prior knowledge with our training data. So some examples was in terms of prior knowledge is like structure, like a face is composed of, you know, 2 eyes, a nose, and a mouth, and so forth. So how to go about combining this prior structural knowledge with training data. Of course, there has been a lot of interest in bridging the two kind of fundamentally different areas of AI, you know, the symbolic AI and connectionist AI together. I think that's still a frontier area of AI, but I think it's also of importance in terms of validation, right? It's a lot easier to validate smaller components in isolation and then synthesize them together. I'll pause here to get general feedback on this idea. It was something that we said that would be really nice, but there's still a lot of research to be done. Yeah, John.
Yeah, I just mentioned there was the presentation of Bowley where she tries not really on the input but more on the output to add let's say like hierarchies between the different classes. So it's more difficult for an adversary to be, let's say, compatible also in the hierarchies of classes that you have. For instance, you have animals and a horse, for instance. If you fool the horse, then you need to find something that is also compatible with the animal, for instance, class or something like that. So you add structure, you add constraints between your class, and yeah, maybe you can find it's more difficult to fool, let's say, the full hierarchy of classes, let's say. So yeah, maybe it's one way, but it's adding a domain knowledge on top of it. It's a way to do it. I'm pretty sure there are other ways, but yeah, I found that quite interesting. It's a shame that she could not connect, because that she could have brought something to the discussion, I think. But maybe one way to look at, maybe.
So maybe we can go back to the more general themes. But we covered the first one, adversarial attacks, a true threat to real life applications. I think the conclusion here is we need to rely perhaps less on P norms and really think about the appropriate ways to formulate robustness. One part that maybe we should probably spend a little bit more time on is actual industrial qualification and certification. Are there folks here who can speak to some of their experiences? I can speak a little bit about our experience with the certification of ACAS-X or standardization of ACAS-X. So ACAS-X is an aircraft collision avoidance system. It came out of my work starting in 2007, but it quickly grew to expand to a number of organizations: Lincoln Laboratory, MITRE Corporation, Johns Hopkins Applied Physics Laboratory, and so forth. And I think one of the major takeaways I had from this experience is that there's no one silver bullet in terms of validation. I would say roughly running a whole bunch of Monte Carlo simulations that were representative of the airspace, that probably got us maybe about, I don't know, 65% of the way there in terms of building trust. We also had a baseline system that we could compare against, that of TCAS, not to be confused with the MCAS system that led to the grounding of the Boeing 737 MAX 8 and MAX 9 aircraft. But we had a baseline, and we spent a long time trying to figure out all the different metrics that have been used historically that the various stakeholders care about. So for an example, how often does the system tell the pilots to change the direction of the aircraft and so forth? And there were dozens and dozens of these different metrics. We also evaluated those metrics on a number of different models. So we had a US airspace model, there was a European model, there were stress testing models, there were models of specific scenarios like approaches to closely spaced parallel runways and so forth. And we ended up running tens of billions of these simulations. So Lincoln Laboratory has kind of a major supercomputer, and we were one of the major users of that system. And those Monte Carlo simulations were pretty core to the safety case. We also looked at formal methods, different stress testing methods, of course, flight tests and so forth. And it's really the combination of all of these different analyses that led to the broad consensus that this system is the way to go. Of course, this is one system that we really didn't want to mess up, right? You can't afford to ground all of the aircraft in the world to fix a bug or a vulnerability. And so that involved cross-checking models and so forth between different organizations from different countries and so forth. For many other applications, maybe the stakes are not as high, and so something as comprehensive might not be as required. But I think in general, working with multiple different tools to validate your system is a good way to go. Any other experiences people have had? Maybe working with systems not within aerospace or automated vehicles?
So Mykel, can I ask a follow-up question?
Yeah, good. Go ahead.
So the scenario you are describing, are you trying to verify a local state, a given state, or the whole system, right? So there's always a notion of local robustness certificate versus like model level, like global robustness. So which level are you looking at when you do this Monte Carlo simulation?
When we do the Monte Carlo simulation, we're actually looking at the execution of this system over time. So one thing that I should clarify up front is that this discussion has largely focused on like neural representations of models. For ACAS-X, it was table-based, although we also explored neural network representations as well. And what we wanted to do was validate that the system is actually safe when deployed in the airspace. So does it actually prevent these near midair collisions? And the system doesn't have complete control over the aircraft. In Boeing aircraft, it provides an advisory to the pilots, and it's up to the pilots to maneuver. For Airbus aircraft, there's an automated response that a pilot can override and so forth. But central to the validation of this system required modeling the behavior of pilot responses.
Okay.
Okay, so
the pilot remains in command here. Of course, we want, so you can view it as a decision support system, at least in Boeing aircraft, semi-automated system in Airbus aircraft. But that said, we don't want the system to mess up, right? Because of the time horizons that we're talking about here, and the fact that it takes a while for the aircraft to maneuver in response to the pilot inputs, right? There's only so much you can accelerate the aircraft. You can only accelerate at, you know, a quarter G or a third G and so forth. And so there's a huge pressure to just get it right. The other thing is that the system has to coordinate between aircraft, right? You never want both aircraft to climb or both descend, right? Actually, there was a situation over Überlingen, Germany, a little while ago involving TCAS, where TCAS told the pilots how to maneuver, but an air traffic controller instructed the pilots on board one of the aircraft to maneuver in the opposite direction. They ended up colliding with each other. And so, sure, in the end, it's up to the pilots, but really, we can't fully push the full responsibility to the pilots in the end because of these timing issues and coordination issues.
And then, John, if you want, you can just proceed, and then I ask the question afterwards.
No, it's just what you described. In fact, there is no AI or machine learning in the system for the moment, because maybe I'm wrong, but you use simulation, you use modeling, but there is no neural networks or machine learning. You have that to replace the table to gain space or, I don't know, memory or time to proceed. But have you also certify the neural network instead of the table?
Great question. So I think that there are two parts to this. I'll address the first part of your question first. So the statement, there's no AI in ACAS-X. So there's no neural network in the certified version of ACAS-X.
That's
but the process that we use to generate the lookup table comes from a solution to a POMDP, and to arrive at that solution we use dynamic programming. We apply. So it's up to you to decide whether you would count, applying dynamic programming to a POMDP AI. I would say it is. There are also probabilistic models that are embedded within that POMDP. That's learned from radar data. The validation models are also learned from model data. But for the neural network work, we did explore the use of neural networks for compressing the table. And this is actually what led to the work on ReLUplex. We were originally exploring this for the version for unmanned aircraft, a flavor of ACAS-X called ACAS-XU. That actually became a standard about, I don't know, 6 weeks ago or so. There are a couple other standards that will come out soon. One for small unmanned aircraft. So XU is for large, like Global Hawk and Predator style aircraft. For SXU, that's for smaller aircraft. It has, which may be more memory constrained. And we're still exploring possibilities there, but there has not been anything certified or standardized involving neural networks. And you can imagine working with the FAA and the International Civil Aviation Organization. These are organizations that are incredibly risk adverse, and it is good that they're risk adverse. I am very happy that they are risk adverse. So much of modern society requires safe air travel. Giant, did I answer the second part of your question, or
yes, thank you.
Have some follow-up there?
Yeah, thank you.
The topic that we discussed involving runtime monitoring, I think that's going to be really important in aerospace, especially with the proliferation of unmanned aircraft.
Mm-hmm.
With unmanned aircraft, it would be great to be able to use machine learned components. But even outside of that, it would be nice to have a runtime monitor, so that a certified runtime monitor, so that we can incorporate perhaps untrusted controllers or open source controllers like Ardu Pilot or one of those that you can find online, but still provide some hard safety guarantees through runtime monitoring.
Yeah.
Yeah, first of all, I would like to thank all the panelists and you, Mykel, for really animating that with a very a nice way. I really found the discussion very rich, and this is really great work from all of us, in fact, because everybody participated, and that's a key point. So thank you again to all of you.